Hi, this is Matt O'Donnell at the University of Washington. Thank you for inviting me to give this lecture. I also want to thank the IEEE UFFC Society for the distinguished lectureship, which is allowing me to give this lecture over the next 18 months around the world. We're going to talk about this integration of light and sound, so with photonics and ultrasonics. And three examples. So first is where light generates sound, and that we'll use photoacoustic imaging to describe those effects. The second is where light detects sound, and this is used for non-contact detection of ultrasound, and we'll look at it for laser ultrasound, but also for a photoacoustic system as well. And finally, we'll talk about where ultrasound tickles light, so where sound modulates light, and the example we use for that is optical coherence elastography. So let's get into the first of these, which is photoacoustic imaging, where light generates sound. So for those of you who don't know the photoacoustic effect, it was discovered by Alexander Graham Bell, yes, the telephone inventor, in the late 19th century for something called the photophone. The way it's used in modern systems is the opposite of the way in which you do traditional optical imaging. And that is that you will illuminate an object with a very, very broad spatially, so not spatially compact, not focused, but a diffused light source into a medium, and typically a highly scattering medium where you don't have to worry about the coherence of the light source. But unlike traditional illuminations, this is time modulated pulse, and these pulses are typically in the nanosecond range. When this light propagates and diffuses into this object, anywhere there's absorption, there can be an absorption, there can be a localized heating. And so for the example shown here, let's say we have a 50 micron black bead, so it absorbs all wavelengths. And so when that light is absorbed here through thermal expansion, there's a slight change in volume in the region. Because this light is time modulated, that creates displacements, derivatives, time derivatives of that, which are particle velocities, which through the acoustic wave equation gives us pressures, which can propagate out. And those pressures can be detected on a traditional ultrasound array. Again, if you put this in the nanoseconds to tens of nanosecond ranges for the lasers, you'll have in the megahertz to tens of megahertz worth of ultrasound frequencies coming out, which is right in the traditional medical range. Now that effect is described by a simple wave equation. On the left is just a propagating wave, so it's a free wave on the acoustic pressure, and the C here is the speed of sound. On the right-hand side is the drive term, which is proportional to the coefficient of volume expansion, or volume coefficient expansion, the heat capacity, and then this heating term, and in particular the time derivative of the heating term. And the heat is proportional to the product of the light, the amount of light that gets there, which is the fluence, to that object, and the amount that it absorbs, which is the absorption coefficient. So remember that, because we'll come back to that later. The fluent product of the fluence and the absorption coefficient. Why is it interesting fundamentally to us ultrasound types is because it can provide optical contrast in a ultrasound image. That is, the imaging part is very similar to what we do in real-time ultrasound imaging, but now the contrast mechanism, rather than being acoustic, is optical, and gives us reasonably large penetration depths from the optics point of view, because as light goes into tissue and diffuses within a millimeter or two, now we can get beyond this diffusion limit and look at centimeters inside the body. So what this effect, what the photoacoustic effect does, is spans the worlds of optical imaging, which is typically in millimeter scale penetrations, but down in micron scale resolutions, up to the ultrasound world, which is in centimeters and tens of centimeters even in penetration, but resolutions in the hundreds of microns to millimeter range. Where photoacoustics works is spanning this range, because we have the optical penetrations, which are typically a few centimeters, nowhere near as much as in ultrasound, but still for many applications useful as a few centimeters. But now our resolutions are going to be the hundreds of micron scale, and this sweet spot is what we're looked at and what we've called integrated PAUS, photoacoustic ultrasound, PAUS imaging, which is in the sweet spot which overlaps between traditional biomedical ultrasound and this pulsed optics for looking at things in centimeter scales inside the body. Why is it so interesting? Well, optical contrast. And optical contrast means that we can use molecular contrast agents, such as are analogous to the fluorophores, which have been used in optical imaging to monitor molecular processes for decades. So now, and this is just a range of contrast agents developed both in our lab and in our friendly competitors' labs, and it's all based on this idea of being down at the nanoscale for the dimensions of these contrast agents, so looking at true molecular events, but getting a readout, which is acoustic, and therefore it can be relevant for clinical applications. This is just an example of one contrast agent recently developed in our group, where we show, and it's actually a mixed agent, has both an ultrasound and a photonic component. Why we've designed this, it gives tremendous sensitivity. So at picomolar concentrations of this agent, we can see down to many centimeters. This is a phantom, but with an optical scattering phantom similar to what you have in the body. And here we can easily 3 to 4 centimeters down, we could see very small scale concentrations. And of course, to demonstrate this agent, we had to sweep out a block W because we're from Washington. So anyway, this is the hope that we have of bringing optics to photonics and this photoacoustic effect, because it gets you into the molecular world. But trying to now translate on this promise has some issues and some practical issues. Now, many applications require real-time frame rates, and that means you must interleave the photoacoustic images at high frame rates with high frame rate ultrasound for it to be appropriate for clinical applications. The second piece is about the size and scales of the systems. The ultrasound industry is moving towards very, very small, these handheld even types of systems, but certainly small cart level or laptop level systems. And an expensive and bulky laser is not appropriate. This is the laser. On the left is the modern generations of handheld ultrasound scanners. But on the right is the laser we use to make the images we showed in the previous slide. So there's a nice Sharpie pen, which gives you a scale. This is the pump laser. That's the OPO, which allows you to sweep wavelengths. That's the controller. And there's a cooling system. And that's what this tube goes down to underneath the optical table. Huge systems, very bulky, very expensive, and certainly not compatible with portable ultrasound systems. So we must get around that. And then the last piece issue that's driving clinical adoption is the optical system must be seamlessly integrated with a handheld ultrasound probe. Anybody who's done clinical real-time ultrasound imaging knows that the real-time aspects allows you to manipulate and move the probe around, and having a clumsy, fixed optical delivery system is not compatible with that environment. So the optical delivery has to be fully integrated with the probe for it to be clinically useful. So our approach for addressing all of these issues is a system we've developed over about the last 7 or 8 years, which is based what we call a fast scanning approach. Rather than having a broadly illuminated single laser pulse, we bring pulses into a collection of fibers, 20 fibers in our case, and rapidly scan optical excitations, pulses among this fiber array. Each pulse produces produces sufficient fluence, actually peak fluences at the surface comparable to the big lasers, which it diffuses more readily because it's from this smaller source, but we get to do multiple measurements. So that means the peak energies we need each individual fiber go down. So that can change the size and scale of the laser. It has to go fast, but it doesn't have to be anywhere near as powerful as the big laser I just showed you. So the first generation of this system that we built scaled from that laser system to this laser system, which was done in collaboration with our friends at the company called Laser Export. It's a diode pump solid state laser. It provides a single wavelength at 1053 nanometers, but functions at kilohertz pulse repetition rate. And instead of hundreds of millijoules, we get about 2 or 3 millijoules, but at this kilohertz rate, which is ideal for doing this fast scan concept. Okay, with this laser, what can you do? Well, this is just showing an example of how you can add a molecular feature to a traditional ultrasound system with the photoacoustics, but appropriately modified for a clinical environment. This is a standard ultrasound monitoring of drug injection. So here comes a needle that's in, which you can see in the ultrasound. You inject a drug, but in ultrasound, you cannot see that drug because it's molecular scale. And then you will remove the needle, and you assume that the drug went where the needle went. And I'll let this play again, is that what we've done is just added a real-time photoacoustic capability, and we just superimposed a real-time photoacoustic image on top of the real-time ultrasound image. But now the drug is labeled. It's labeled with polypyrrole, which is a polymer, nanopolymers, which labels at the molecular, which is a high optical absorber. And so it can label the drug so you can see exactly where the drug is. And even more important is once you've removed this, after you can see what the drug is, you see how the drug can diffuse, see how the drug is utilized, etc. And so it brings this molecular scale to this. Okay, the next stage in this evolution was to go from single wavelength to multi-wavelength. And that's shown here, again, working with our friends at Laser Export. This is TiE Sapphire, a tunable laser, but being pumped now by one of these guys. One of these diode pump solid state lasers acts as the pump to a TiE Sapphire, tunable TiE Sapphire laser. That laser is electronically tunable with electro-optic devices, which means from pulse to pulse to pulse, we can have this high repetition rate at slightly lower energies than the other ones, or rather a millijoule. But from pulse to pulse, we can arbitrarily pick a wavelength between 700 and 900 nanometers. And this is used so we can do spectroscopy, which is sort of the crown jewel of optical imaging, is because through spectroscopy is you can do molecular identification. So you can see and you can infer different species, blood, oxygenated versus deoxygenated blood, different types of contrast agents, different types of materials, lipids versus water-bearing materials. All these things can be done through spectroscopy. So we've built, just in the last couple of years now, we've put together this complete system, which includes ultrasound scanner, this high-speed laser, the fast fiber delivery system, and this is shown here. And we've used it for experiments, but also what we've found is that this approach can overcome two major problems which limit the potential clinical applicability of spectroscopic imaging. And those two issues are, first, motion. No matter how fast you go, if you have a collection of wavelengths over which you are going to get spectroscopic information, you can be subject to motion. And this just shows how when you have a reference spectrum, which you're trying to tune to, that molecular signature, that when there's motion, so particular sources can move in and out of an imaging voxel, is that you can corrupt the spectrum and therefore make spectral misidentification, so major artifacts in your image. The second confounding effect is that, remember that the photoacoustic signal is proportional to the product of the fluence and the absorption coefficient. Now, in most imaging, you assume that the fluence is constant with wavelength, but it is not. In reality, it is very wavelength dependent. And so when you scan over a range of wavelengths, again, you can shift and color the true spectrum, depending exactly where in the imaging field you are, because the fluence is a function of position and wavelength, and therefore must be compensated. What we have found in putting this whole system together, and this is just in very recent studies, is that we can integrate, once we integrate this whole thing together, we can create an interleaved pulsing sequence between moving those laser firings around to the different fibers while interleaving our ultrasound measurements and changing wavelengths from frame to frame, is that we can get simultaneous and perfectly registered in time and space photoacoustic images in ultrasound. And then we use traditional speckle tracking on the ultrasound, it is motion estimation in the ultrasound, to compensate and re-register the photoacoustic images to get spectral purity. Similarly, for the fluence compensation, because we illuminate the object from different regions, if the object is fixed and the the optical source varies, we can model the signals that we obtain and estimate the laser fluence, and from those estimates, spatially localized estimates of the fluence, compensate for it so that the image produced is simply proportional to the optical absorption coefficient only. So let's repeat that simple ex vivo drug delivery experiment, where now we're going to use a gold nanorod labeling of the solution. So in comes the needle, you inject the agent, but now we're sweeping wavelengths during this. So that's what it's just showing. As you're doing this experiment, you're sweeping wavelengths at different periods. So when we're inserting, after the injection, and once we finally pull out, so you can do a spectroscopic identification. The type of information you get is you get these registered and Fluence corrected images at the different optical wavelengths. You then, on a pixel by pixel basis, can put spectra together and compare the spectra, for this example, in a region which is clearly dominated by the gold nanorods, compared to other regions such as these, which are dominated by the needle, is that you can separate those doing a spectroscopic projections, very simple linear algebra, to get images of individual components. And so here you have now, when you're bringing in the needle, this is your gross photoacoustic image. This is just the sum over all wavelengths, so equivalent to a single wavelength type of photoacoustic image. What we see is that the projections, there's no gold nano, which is good because you haven't injected anything yet, but you can clearly see the needle. During the injection, you can see both where the agent goes as well as the needle. And finally, when you pull out the needle goes away, but we see agent. And note that we're bioengineers, not physicians, is that when we pull that needle out, we pull the track of nanoparticles with it throughout, and we know that it's not the needle because it's projected as such. Okay, so now we look at the same sequence in vivo. Now, in vitro, we really didn't have to do the motion correction. It's more the Fluence compensation. But here, we need both of the motion correction and the Fluence compensation. And so we do that again. We have the images registered. So now when they're unregistered, that is uncorrected, we get a compounded image like this. However, once corrected, we then look at the spectroscopic projection, and we see it's a perfect projection to the nanoparticles, and this is done after the needle has been removed. And what we see is a image where now, and as validated post-experiment, is you see the exact distribution of the gold nanorods where you were delivering them in this in vivo small animal model. So that gives you a picture of this first. When light generates sound photoacoustically, and the primary motivation, again, is to bring this molecular feature, a beautiful molecular feature of optics, optical spectroscopy, into a clinical type environment using an ultrasound system, and we're working on developing these real-time PAUS systems to do exactly that. Okay, let's go to the second one. This is where light detects sound. Okay, and the first part we'll talk about is systems of laser ultrasound, then we'll talk a little bit about a photoacoustic system that uses this principle. But the primary principle is that we're going to detect sound with a non-contact fashion. We will not detect the object by using optics. So how do we do that? So in a traditional laser ultrasound system is that you will bring in a pulse laser, just like we talked about in photoacoustics. However, now that laser is tuned to a wavelength that for the object of interest, all of the energy is absorbed at the surface. So that efficiently launches an acoustic wave into the material. Then reflections, backscattered ultrasound signals, come back to the surface, and those vibrations at the surface can be detected optically using an interferometer in there. And this type of system has been around now for several decades to do this for using ultrasound in a non-contact fashion, and it's used in non-destructive testing and some other in aerospace and transportation industries. Okay, now I'll just mention this briefly, and happy to talk about it in detail afterwards if anybody's interested. But this technology has been around for a long time, but our major approach to this was to take the interferometers, standard interferometers, which were used for this, which were highly insensitive and very unstable. And we developed a replacement for that, which is based on the Sagnac principle, which removes the reference arm of a traditional interferometer. We use the same path, optical path, for both sample and reference arm, and use time delays through polarization manipulations and integrated optics to provide the interferences needed for making the measurements. This is several orders of magnitude more sensitive and several orders of magnitude more robust than traditional optical detection schemes. And so we've been able to use this as a very sensitive tool to look at things in non-destructive testing, as I'll show you in some biomedical applications as well. But again, just briefly said that in about a minute, but happy to go into details with people of how this interferometer works and why it is so sensitive and robust compared to previous systems. So our first application was actually non-medical, and it was just because of a friend's contact anyway, but it was about to inspect composite materials. How can you, in the field, be able to inspect composite materials, which is where modern aerospace is going, so like the 787 aircraft from Boeing, when you have an impact event like this. And you just saw that, I'll let it play so you can see it again. But this is not atypical. In fact, there are, on average, for the worldwide fleet, once per year, that every aircraft has a significant impact like that you just saw in this. Now, usually it can be a lightning strike or a flock of birds or a vehicle or the docking stations, so the bridges to come in to take you off, the gangways to take you off. But on average, once per year, this happens. And it's not clear what to do after the impact. When it's metal, you can look at a surface inspection, know pretty well what's happened in the interior. For composites, you don't know. And that's why it's such a great desire to have a non-contact rapid inspection system that can be used in the field. So we've proposed this laser ultrasound system to do that with this double differential Sagnac interferometer. And the approach is, so just so you can understand some of the images, the A-scan, like in traditional ultrasound, which is a pitch catch, and you just look at reflected echoes with depth, so time is depth, and so you get one dimension profile of reflections from the object. If you now scan source and detector simultaneously together along a line, you can get cross-section of vertical cross-sections, which are B-scans. If you sweep out those source and detector in a 2D grid along the surface, you can get three-dimensional images, which is what we do. And I will show you displays here where we show these three-dimensional ones as a set of C-scans. So that is horizontal cross-sections, but with time, is like we're going through depth. So we're going vertically through the object. So it's just a 3D visualization tool. But you can think of them as cross-sections, and then we're just scanning through them with depth in the movies that I'll show. So remember we talked about the impact. So the primary thing we're looking at is impact damage. And this is a simple test case of a test composite. When you drop a ball bearing on it, it's a 25 joule impact. On the surface, damage you can see is very, very small. We then looked at that scanner in place, just looking at the part that was damaged, scanned this, and this was done a few minute scan over this area, and we compared it to micro CT. Now, to do micro CT, we had to cut out this area from the sample, bring it to a CT facility, wait a few hours, and got these images. So this is a destructive testing that took several hours, but is the state of the art in high resolution imaging of composites. And this is our little ultrasound, non-contact ultrasound scanner taking minutes to do the same thing that this took hours to do and compare. So remember, as the movie plays, you're going to be going through depth and looking at horizontal cross-sections. So here it goes, and you can see the damage, and the damage is much more extensive in extent than the surface depth. And you can see, and we allowed it to integrate here, you can see the entire region is much, much larger than you see in the impact. So this is why having a tool that can go out in the field and do this non-contact inspection could be incredibly important for composites. Now, I'm a biomed guy, so of course we originally developed this looking for biomedical applications. We've looked at three so far: cytometry, which is label-free, that is, we don't use fluorophores; digital pathology, again, without any labeling, and it's a photoacoustic; and scatter-free spectrophotometry, which I'll spend a few minutes on to tell you about here. Okay, so spectrophotometry, if you're not familiar with it, it's a gold standard for looking at molecular profiling of solutions, because between specific molecular species, for specific molecular species, there is almost always a unique optical absorption spectrum. And so from a composite optical absorption spectrum of a solution or a set of materials, is by looking at the combined optical spectrum, you can decompose it into its components, similar to what we talked about in the photoacoustic imaging in the first part of this. So a traditional a spectrophotometer, though, is very simple. It has a light source and detector. It sends a broad beam through a medium. And here I have some stylized or cartoonized nanoparticles, which are in there. This is the absorption spectrum of the nanoparticles. And if you have a dilute suspension of these guys in a solution, you can clearly get a robust measurement of the optical absorption spectrum. However, what if you want to look at, and let's say it's nanoparticles, and to see how they are taken up by cells? You would like to see how these work in the cellular environment and to see if these optical characteristics change. However, when you get into a medium, such as in a cell culture medium, which has high optical scattering, is that the relationship between this through transition measurement and the true absorption is confounded by the large degree of scattering. Now, there are some approaches to using reflecting spheres and others which can capture that scattered light, but they're very, very sensitive systems, have to be calibrated for almost any kind of a particular type of sample you use, and can be complicated, very, very complicated systems to use. So we looked at an alternate approach using our friend photoacoustics, but to be able to do it in cell culture, we couldn't bring in an ultrasound transducers to do that. So we developed an approach which leverages what we learned from this non-contact optical detection. And that is we bring in now, so if we have well plates of, for cell culture, and cell culture, so in cellular media, is we can deliver the tunable pulse laser for doing spectroscopic measurements, and the generated acoustic signal is then detected from the bottom of the well plate using this non-contact optical detector. Okay, and so what kind of results we get? So here's a very simple test case that just shows the potential power of this instrument. Here we have cells, and they're HUVEC cells, human umbilical vascular endothelial cells, which are just in solution with some nanoparticles, which maybe you're going to use for some therapeutics. Because they're just in solution, if I look at the optical absorption, the spectrophotometer measurements, is they're a little complicated because of the scattering, like we said, but when you take simply the difference between cells without these particles in their solution and those with the particles, is just a simple subtraction of the absorption spectrum. It's fairly similar to what you get from the true absorption spectrum of the gold nanorods. You see it's just broadened a bit, but its spectral characteristics are very similar. However, for the case in which you're most interested in, that is when these nanoparticles are endocytosed. So for example, if you were doing drug delivery, what happens? Well, if we put them in a spectrophotometer, again, we do without particles, with particles in the cells, and we just take the subtraction between these two. It's nothing like the true spectrum. So again, the blue guy here is the true nanoparticle. And so you have no clue about what's going on. However, that spectrophotometer, photoacoustic spectrophotometer measurement is shown here in red. Okay? And so let's look at that just a little more closely. So here's the subtraction of the spectrophotometer results. It has nothing to do with what's going on with the particles in the cells. Here's the true particle spectrum. But now you can look at the true spectrum within the cells. And what you can see is that there's a split. There's a red shift and a blue shift of the gold nanorod spectrum. And that has to do with plasmonic coupling. The only way that you can see this within living cells with an optical technique is to get one that gets rid of optical scattering, and that's photoacoustic. So the combination of a photoacoustic spectroscopy measurement with a non-contact detector is an ideal approach. So with the second part of this, we've talked about lasers and optics for detecting ultrasound, and we've seen that in two environments: laser ultrasound systems, which are most appropriate for non-destructive testing applications, and for non-contact photoacoustic spectroscopy, which can be done in tissue culture for the spectrophotometry. Okay, so let's go to the last part, which is where sound tickles light. And the concept of this is optical coherence elastography. And in this, as we'll see, we use OCT, optical coherence tomography, as the imaging source. So ultrasound will not be involved in the imaging. However, we're going to use ultrasound to modulate the tissue in a way which will be detected by the OCT system in order to look at the elastic properties of tissue. Okay, what's the motivation? Is we're trying to assess, of this approach, is to assess the biomechanical properties of tissue without any contact. Okay, so the OCT system is fundamentally non-contact, and by trying to produce a deformation and then watch how that deformation propagates, is we can assess the corneal, the properties of sensitive tissue such as cornea. So we can look at difference between normal refractive surgeries, either before or after, and for advanced diseases, or to try to mitigate advanced diseases such as keratoconus. You can also look into skin, and we're working with burn surgeons and reconstructive surgeons at University of Washington, where you cannot assess elasticity of the skin, but the elasticity of the skin is very important for transplants, but you cannot do that in a contact fashion, and so our non-contact approach they're very interested in. And the last area, which we've looked at a little bit, but hopefully are going to spend more time on, is small, delicate samples. And the ones we're most interested in right now is organ on a chip and watching the evolution. So, for example, the evolution of connective tissue on a chip, and being able to with non-contact, non-invasively monitor changes in the elastic modulus as that tissue develops. Okay, so corneal biomechanics. Let's focus on that for the first part of this. And remember, to remind you that the cornea is the primary focusing lens. Its shape, which determines its focusing characteristics, is determined primarily by the intraocular pressure and the elasticity of the tissue. The clinical standard of care, though, is simply to measure the shape and the IOP, and that's done through a classic forced deformation curve. Of course, it can be in this contact way, but we're trying to avoid the contact at all, because if any of you have had those types of tests, which I have had, is you have to have a little local anesthetic to be able to have those tests. And they're still compromised because they're trying to look at shape and IOP, but they assume a sort of uniform elastic modulus for the eye, which is not appropriate. Okay, so our goals were three. That is, we want to quantitatively map the elastic modulus, because of course, as part of this fundamental characteristic of the cornea is that the shape is the IOP and the thickness and the elastic modulus. So we want to quantitatively map the elastic modulus. We want to measure the IOP, which is independent of any assumptions about the corneal elasticity. And finally, to guide and optimize therapeutic interventions for things like keratoconus and refractive corrections. Okay, but in the limited time left, I'm only going to talk about quantitatively mapping the elastic modulus and our approach to that. So 3 steps. So this is like elastography in both MRI and traditional ultrasound, but this is trying to be done with no contact. So you're trying to make mechanical waves and watch them with no contact. So the first you need is non-contact imaging that we have with our friend Ricky Wong, a collaborator in UW Bioengineering, who has a world expert in optical coherence photography, especially for being able to sensitively measure displacements. So it can measure displacements in nanometer scale. Resolution at microns can be, for what our application, usually 10 to 10, 20 microns is the kind of the typical resolutions, but sensitive to displacements at the nanometer scale. Quantitative. We're just leveraging the work's been done in ultrasound and MRI elastography, and that is dynamic elastography, in which an excitation launches a shear wave that's propagating. In bulk materials, there is this simple relationship between the shear modulus and the wave speed. So by mapping the wave speed, we nominally can match the shear modulus. And in incompressible materials, the Young's modulus is simply proportional, is roughly 3 times the shear modulus. And so therefore, you should be able to predict deformations by able to image these moduli. Okay, so we're going to image. All right, we're going to be quantitative by mapping these propagating waves. How do we create them? So we need a deformation source. Well, as I showed you, there's a number of different types of deformation. Ways to make the deformation. One of which is ultrasound radiation force, which would be great. because it's a propagating wave. But unfortunately, traditional ultrasound must propagate through water or some tissue-like medium or a gel, which creates contact, which is inappropriate for the skin and eye applications on which we're focusing. We have looked at a number of non-contact means, air puff, which is used clinically, which again is just a little too crude in terms of its temporal response and spatial focusing characteristics. And so it's sort of a crude tool, which is not appropriate for the high resolution imaging we're talking about. We then tried our old fit, photoacoustics again, and used pulsed UV light, which gets absorbed in the first microns of the cornea, to launch one of these mechanical waves. And we showed that and published papers on it, but it's very inefficient. So we looked at another one and said, go back to ultrasound. Why can't we use ultrasound? If we can use it, if we just change the medium, and the medium for us is going to be air. And the fundamental mechanism, as opposed to attenuation-based radiation force, we're looking at reflection-based radiation force. And that is, if you launch a wave in air, which is perfectly reflected off the surface, we will get a transient force here, which creates this displacement, which can propagate. And what's interesting is because it's reflection-based, it's almost a perfect force transducer. So you go from acoustic intensities to mechanical forces very, very efficiently. Just to show, this is known, this is a commercial transducer functioning at a few hundred kilohertz, and just showing how you can move around some salt very easily. These forces are quite substantial, and certainly for the nanometer scale displacements we need for our OCT system are easily done. So that's what we did, is we went in the business of fabricating air-coupled transducers working in the 1 megahertz to 2 megahertz range, so we can get the spatial selectivity that we need. And integrated that with an OCT system to image the propagation of mechanical waves in the cornea. So if you're in a bulk, this is just a simulation, but showing what like one of these measurements would look like. So when you put the force down right here where the air-coupled beam hits the surface, you'll create a surface wave, and propagating at an angle out is a bulk shear wave, and this angle is fixed. It's determined by the characteristics. Primarily for incompressible material, that angle is fixed for all materials. So you have the surface and shear wave. If you map these and find their wave velocities, the bulk wave we said was simply proportional to this, but that shear wave just has a simple fixed constant, and so the speed of that can be used also to find the shear modulus. Okay, so wave speed estimates. The way you do it is you just track this wave. So if I look on the surface, for example, I can do this in the whole volume, but if I just look at the surface, as a function of time, I'll see I have this simple linear relation here. And by locally estimating the slope, I can get the speed, or by doing a fit over a large region, I can get a very accurate estimate of the wave speed in the medium. Okay, so we did that. So we built a system that combined these through the transducer, Ricky's real-time OCT system with our ultrasound system. So the images I'll show you is that to acquire the full volume of data for the propagation of the wave across the cornea is about 1/3 of a second. I will show you movies which are the slower frame rate so you can actually see the propagation of the wave. And so here we go. And this is just comparing the excitation for a pig cornea, which was one subjected to 10 millimeters of intraocular pressure versus 40. And as you can see, I'll just look at this one more time, you can see that wave speed in the 40 is much, much higher. And we show that here, looking, these are results published from our group, that when we compare, we can see these differences in wave speed, therefore presumably differences in effective modulus with the intraocular pressure, which is not unexpected since tissue is a nonlinear material. Its modulus increases with applied load, so you expect the wave speed to increase, and it does. But we can also map these, as we did three-dimensional, make images, compare, everything looks fine, right? Hunky-dory. We do that's the same thing in skin. So we look structurally at the images and just comparing different sites in the wrist versus the palm of the hand, and you can see structural differences, but also wave speed differences. When we map these, we can compare structure and elasticity to this. And again, we're working with some reconstructive surgeons about transplants, trying to guide the proper selection of host and donor material, well, of donor materials in terms of elastic properties. Okay. And that's what I said, this is where we're working now, is trying to put together a real-time robotic system for doing this for clinical applications in the burn center. But wait a minute, okay? Is it really this easy? No, as you might expect. In fact, when you go and take these wave speed measurements, estimated elastic moduli, you say, oh, these should be quantitative. That's what we were arguing before. It should be quantitative. However, when we quantitatively compare those to biomechanical measurements, they're not copacetic. Okay, and why? Well, we have complications, or as a native New Yorker, I would say problems, problems, problems. There's a whole bunch of these. In the remaining 5 minutes or so, I will look at the two primary ones which we've attacked recently, which is a guided wave behavior. Namely, in the cornea, we're looking at very thin layers. Also with the skin, we're looking at thin layers. And we can't use this bulk analysis for doing that. And the second piece is tissue anisotropy. That is that the elastic moduli are not isotropic everywhere. They do have directional dependencies. Okay, so bounded versus bulk. So it's just noticing, as instead of the infinite medium, we have this bounded medium. If you remember what we had in the bounded medium, we had these surface wave and shear wave. We take the XT plot, we get the speeds. You do that same experiment in a bounded wave of dimensions of about the cornea, you get a much more complicated wave behavior. When we just look at the XT plot on the surface, we can see we do not have these simple linear, perfect linear lines. We now have this beating pattern, which is a result of the interference between multiple modes which are able to propagate. All us ultrasound people know about this stuff, but now at these lower frequency ranges, mechanical waves, is the same type of analysis applies. How do you account for these multiple modes? We do dispersion analysis, which for us is taking two-dimensional Fourier transforms. And so we can look in K frequency space and identify individual modes. As it's shown here, which is a little bit simpler to represent, we look at wave speeds versus frequencies, and we can see these dispersion. And from that, rather than not knowing exactly where we are, if we do the full dispersion analysis, we could then estimate the modulus, and we've published on this. And yes, the result is yes, for the cornea and for the skin, we must do some level of dispersion analysis. However, we got better results by doing this, but they still were not quantitatively accurate. So let's look at that. Let's look at what the actual biomechanical properties of the cornea are. So first of all, the cornea has been characterized in two ways using these destructive types of tests. One is a tensile test, which is a uniaxial force, and this is a direct measurement of the Young's modulus. And what these experiments have shown, in a large number of studies, is on the low megapascal range is the Young's modulus for the cornea. Okay, sheariometry, okay, is a direct measure of the shear modulus itself. When you look at the measurements from the literature again, it's on the order of tens of kilopascals. So let's look at this. The shear modulus can be related to the Young's modulus if you have a perfectly isotropic material, as just by this fixed factor of 3. The human cornea, let's take, for example, about 3 megapascals would be a typical Young's modulus, and the shear modulus is about 25 pascals. 3 times 25, 75 kilopascal, which is well over order of magnitude short, like an order and a half magnitude short. It doesn't, and so there's way off, which is why you can't relate these wave speed measurements to biomechanical deformations, because the deformation of the cornea is primarily determined by the Young's modulus. So is the cornea isotropic? No. It's a model, and so it's a model which is lamellar sheets of collagen, and an isotropic elastic modulus is not appropriate for this. We have looked at something which we call a NITI model, or a nearly incompressible transverse isotropic material, where we have the shear components down here are replaced. We now have 2 independent shear moments, one which is an in plane, which has to do with these lamella, and one which is out of plane. Okay, so G is an additional independent shear modulus. For an incompressible material, however, the Young's modulus is given by this, the mu parameter. However, for torsional force or shear force, it's given by G. Okay, so TI materials allow us to decouple mu from G. That's the good news. But the bad news is, for the type of experiments that we do, which is stimulate here and look at waves propagating laterally in the X direction with the displacement in the Z, this is in the plane of the lamellae of the cornea. The speed of this is determined by that planar constant G, okay? So a knitting material and a bulk knitting material, when we look at these surface and shear waves, which are launched from the surface deformation, we have access to G, but not to mu, okay? So we're not really measuring the fundamental biomechanical. But this is where a bug turns into a feature. We can now look at the dispersion of guided waves in this knitting material. And what happens is that and this is just talking about this, when we look in there, we have, and just look at the two primary modes, A0 and S0 modes, as you have when mu equals G in isotropic. As G changes, both modes change. Now, the S0 mode, the symmetric mode, changes a lot. But as this gets more and more anisotropic, we with our excitation, we put less and less energy into this mode, and so primarily the A0 mode is what we typically look at. And if we look down in this bottom region and just focus on the A0 mode, what we'll see is that as the anisotropy changes, the shape of this changes. The lower part of this is governed primarily by U. The upper region is primarily governed by G, which means that if we can do a wide spectral analysis of these modes, we should be able to separate U and G. And that's what we've done. And so we compare it to an isotropic phantom here, where we see the two primary modes, the A0 and S0 modes, and they fit very, very well. When we go into the cornea, we do not see that. We see just the single mode. And when we try to fit it with an isotropic model, we get a very, very poor estimate, whereas the TI model is an excellent fit. It gives us robust estimates of both of the two moduli. When we do that, we get results which are very, very consistent with the biomechanical measurements. These are results just published. And what they show is that we can, in fact, from these non-invasive, non-contact measurements, get information about the Young's modulus, which should, we are hoping, as we need to prove in the future, can help us to guide biomechanical modeling and guiding interventions. So again, gave you 3 examples of the way we can integrate light and sound together. And so I want to thank the funding sources. The people in red are our faculty colleagues. The people in blue are the most recent postdocs in the group who have helped apply to this. And I thank you very much for your time, and very happy to take questions when I stop.